Okay, so welcome, like I said before, to the 8th annual Mix It Up. This is the second day in our event this year, and it's a film festival. We showed a film on Thursday, and now we're actually showing films that students and faculty created. Each film is related to science in some way. I'm going to be your semi-host today. I'm Regina Barber DeGraff. I teach physics and astronomy at Western Washington University here. This is kind of like rote. This is what I say for the podcast, so that's why I said Western. I'm also the STEM inclusion and outreach specialist for the College of Science and Engineering, and I've been so for this is my 6th year. And I help with this event every year, but the heart of this event are clubs. Every year we have clubs present what they do. They try to recruit more members, and it's more of a community building event. So this is this year we've had about 5 or 6 clubs really help out with this event. They'll be presenting in between the films because I'm going to have to stop sharing and finding the film and share it. So there's going to be about a minute or two in between each film. So they'll be presenting their about their clubs. And I want to give a special thank you. Well, I already said Robert Clark, but thank you again. Robert Clark is the media tech person for the university, and he really helped us with these webinars. But the second person I'd like to say thank you to is Michaela King, who is the communications consultant for the College of Science and Engineering. And she and I have been really doing a lot of the logistics, and she's done the majority of the logistics, figuring out prizes and all this kind of stuff, and helping out our presenters for the last event. So Michaela did an awesome job, and all of the clubs here have just done awesome jobs, which is why they're getting these face masks. And this is our swag from this year. Every year we have shirts, but this year it's face masks. But yeah, all the clubs have done great work, and you'll be able to see the students that have been involved and their club information in between the films. Okay, so if you just showed up, let me just put the list of the films one more time in the chat. If you have questions about the films, right after you see it, go ahead and put them in the Q&A, because some of the filmmakers are here today and might be able to answer your questions. And we will, heads up everyone, there will be a presentation of a first prize, second prize, and you'll have a chance to vote for the viewer's favorite, viewer's choice. It's a pretty big deal. First prize gets $250 worth of stuff from Amazon, whatever they need, textbooks. Maybe we just give them a gift certificate. It's what they want. The second prize is $150, and the viewer's choice is $100. So this is a big deal. If the viewers pick somebody who has already picked first and second, because I'm going to say those prizes first, it goes to the runner-up viewer's choice, because we do want to kind of spread the wealth here. And so just that's the heads up. Please stay for all of the films, because you'll be able to pick who gets $100, basically. So pretty important. Our first film is called Surf Science, and I'm going to play it right now. And I hope you enjoy it, because I did. I already watched it.
I guess I'll do a very quick presentation. I'm Maya. I am from SACNAS, which stands for the Society for the Advancement of Chicanos and Native Americans in Science. We are a student-run club here on campus, and we are the Western Washington chapter of the national organization. You do not have to be Chicano or Native American or even a STEM major to join, but our main goal is mostly to bring diversity to the STEM fields and to allow BIPOC students, staff, and faculty at Western just to have a community space for discussions, advice, just hanging out and relaxing. Aside from those community just hangout times, we also host events like our REU internship workshop and STEM into grad school, which we hope to do this year somehow over Zoom, in order to help students prepare application materials. And we also do some outreach events like the GEMS Fair in spring. We do also attend a national conference every year. This year, it was about a month ago now, online, and it went as smoothly as it could. So that was great to do, but we like to do sorts of networking and make sure people get connected however they might need to. We do meet every other Tuesday evening, 6 to 7 p.m. on Zoom. And our final meeting will be on December 1st. It'll just be hang out, chill, drink your tea and hot chocolate, play some online games, and relax over our week. So if you want to join, I'm going to put our information in the chat and you can see us there or follow us on our socials.
Thanks, Maya. Maya has done a lot for this event too. Just heads up, she did a great amount of work. So I'm going to share the first film, Surf Science. There we go. Let's make that big. And I will mute myself so you do not have to hear my commentary. Okay, I really, really like that end scene where you can see him walking up on the beach and you can see the birds. I really like that part. Okay. Okay, so I don't know if we have that filmmaker here. Let me put his name in here just so you know it's Robert Beck. And he didn't put any credits on that film. So I just wanted to make sure you all know who that is. That's a student. So is there any questions? Does anyone want to? No, yes. I'm going to allow the next club to talk about their club, and then we're gonna set up the next film, which is, what is Light, I believe.
Okay, hi, I'm Julie. I'm the acting secretary for Chemistry Club. Chem Club is Western's student chapter of the American Chemical Society. We are focused on chemistry, but we're open to everybody. We have kinesiology majors, we have physics majors, we have e-sci majors. You just have to think chemistry is cool and you can come hang out with us. We have a lot of social events. We have normally a Halloween bowling night where everyone comes and wears costumes and bowls and competes. We also have trivia night, and we have a spring picnic where we have the Olympics with the chemistry department. We also do smaller, more low-key social events like potluck nights, game nights. Lately, we've been doing a lot more game nights through Zoom. Just last Friday, we had Cook with a Chemist, where we learned a pasta recipe, but we also learned about the chemistry behind boiling pasta, which was really fun. We also do outreach and community engagement, professional development type events. We volunteer with gyms. We do stuff with local schools. We do a lot of demos, all the like classic like elephant toothpaste, fun, messy demos that kids get really excited about. And anyone can have a chance to learn and volunteer and do those demos. And it's just so awesome to get to engage with kids and see how excited they get over science. So if you like talking about chemistry or science in general, or just want to hang out with a lot of different nerdy friends, we meet every Tuesday from 5 to 6. And I'll give that link in the chat.
Thank you, Julie. I just realized that if I don't turn off my video, then maybe that will affect you all watching the film. So I'll just make sure to turn off my video as I start this next film called Light by Addison. And he was actually in a course that I teach, which in the summer, where we create short films, short science films in 6 weeks. So that's the goal of the class. And there's a few of those episodes, or so few of those videos that you'll be able to see today. So let me go ahead and share that screen.
Light. What is it? Science. Okay, so Planck's constant tells us that the emission of electromagnetic energy is not continuous. It is a discrete function, meaning that there is a tiny indivisible unit. A little piece of light he called a photon. And the Planck-Einstein relation tells us that the energy of a photon is equal to Planck's constant times the oscillation frequency of the light. Alright, so light's a particle. That was pretty easy. Well, if light is simply just a particle, then these photons should just travel past each other unencumbered, just like these bits of sparkler do. It would just basically act as a projectile. But an experiment conducted by Thomas Young in 1801 showed a very different result than we'd see if light was really just a projectile. The experiment consists of a light source, an opaque sheet with 2 slits in it, and a sheet to measure what gets through the slits. Now, I'm definitely not a physicist, so let's talk about something that I do understand: sound. When you're in a room listening to music, you may notice that in certain parts of the room, the lower frequencies of the music sound louder, in certain parts where they sound quieter. This is because of something called positive and negative interference. Let's call this top sine wave C, and let's call the bottom two A and B. And C is the sum of A and B. When the high points of A and B are in line with each other, C is just an amplified version of them. But when they're at a phase of 180 degrees, meaning the high point of A is at the low point of B, they cancel each other out, and the sum, C, is 0. And this actually applies to more than just mathematical functions and sound waves. This applies to all waves. We see here 2 bricks dropping into water. The ripples they form are pretty close to sine waves, so even though there's a lot of background noisy waves, we still see a point of positive interference, A, and a point of negative interference, B. From close up, we can see the complex interaction of these waves called an interference pattern. We can see here, after these waves have interfered with each other, there are points of positive interference and points of negative interference. If a water or sound wave were to pass through 2 slits, it would create an interference pattern behind those 2 slits. And this is exactly what was observed in Thomas Young's famous experiment. These little bands of red represent zones of positive interference, and the gaps in between them represent zones of negative interference. Now here's what's crazy about this experiment. It works with electrons too. And even with single electrons at a time, these tiny particles, electrons, are acting as waves, almost as if they know there's supposed to be an interference pattern. So just as ripples on the ocean are a wave of water, and sound is a wave of air, matter itself is a wave of space. There's a lot of cool things about this experiment that I didn't have time to go into. So if you want to get your mind seriously blown, check out some of these sources.
All right, so that was Light from Addison. Yeah, so I have, so it says, I'm sorry, I keep on moving my mouse. I keep on getting these announcements. I really apologize. I will no longer move my mouse. Okay, so the next club, if they would like to present, I'm gonna go grab the next video.
I can go. Okay, so my name is Allie. I'm a representative for Nerds Club. That's neuroscience research-driven students. So our club is pretty much, if you like anything brainy or if you're stoked about brains, feel free to head over. We meet every Monday. We just talk about some cool things. I'll drop some links in the chat for our like Facebook and our Instagram, but we pretty much just learn new things together. Like at the last meeting, we talked all about psychedelics and where they are in the FDA process and just kind of like had a conversation. And then we also do lots of outreach. So before pre-COVID, we would go to local elementary schools and just do some fun little things with like the kids. We would make clay models of brains. We would make neurons with like hands or like pipe cleaners. And then now we actually do that via Zoom. And so we'll go into Zoom and we'll still make those like fun little hand neurons and just do a bunch of like outreach stuff just with the local elementary schools. But yeah, that's Nerds, neuroscience research-driven students. And then I'll drop some links in the chat.
Thank you, Allie. So the next film is about Chernobyl and radiation detection. And it was from Mitch, and I will give his Treadway, and I will give you his name in the chat in a little bit. Let me go ahead and share my screen and not touch anything, even when it, alerts come in through my computer.
When we say nuclear detection technology, what we're really talking about is atmospheric radiation monitoring, just looking in the airways for any signs of radiation that may point to a potential disaster. The HBO miniseries Chernobyl gives us a great example of this, when scientists in Minsk open up a window and their internal dosimeter goes off, measuring radiation coming from outside. This is because that radiation wasn't just at Chernobyl, it was in the air. When the Chernobyl incident occurred, radiation spread across all of Europe and reached as far as Canada. And had there been international awareness, there could have been an international response, where Chernobyl spread could have been limited at an earlier stage. In this pursuit, following the passage of the Comprehensive Nuclear Test Ban Treaty, Pacific Northwest National Labs endeavored to develop the ARSA and RASA technologies to better screen for radioactive isotopes. These technologies are highly technical and hard to understand for a lot of people, so hopefully the following animations will help people understand that in a way that doesn't require them reading this exceedingly dry paragraph. After air is taken in by the machine, it undergoes a series of filters to isolate a specific radioactive isotope, which in this case is xenon. First, it goes through a molecular sieve to remove any water and carbon dioxide in the sample. Then a series of charcoal traps removes other contaminants, and the xenon is gasified and refiltered through silica gel, ascarite, and another molecular sieve that removes any residual radon. The xenon is then absorbed in a final charcoal trap at 250 degrees Celsius, and is then reconstituted in a scintillation detector cell, which generates photons in response to radiation, measuring the level of ionizing radiation using appropriate detector efficiencies. So that's the technology, but how is it being applied? In terms of treaty compliance, one of the biggest uses for this technology is part of the atmospheric radiation monitoring system, where there are hundreds of monitoring stations set up around the world which are constantly checking for radioactive disturbances. Things to catch the Fukushima nuclear incident as it happened in Japan. These incidents are highly dangerous, and so early detection is important so that we can send appropriate teams. While we weren't able to limit the spread of Fukushima, we were able to limit the danger that it presented. But the technology doesn't stop there. It's been employed in the oceans to search for transuranic waste products, as well as at the northern border to search for things like dirty bombs that might be crossing the border. In conclusion, radiation, very dangerous, which is why an early detection system is imperative for our safety going forward. And the technologies developed at PNNO are what give us that early detection system. Thank you very much.
Okay, and Mitch's film that you just saw was also made in the summer class, so I just wanted to give you that heads up. Is there another club who would like to present as I get the next film ready? I'm going to show this one, but we will have another club coming up after the next film. Here we go.
In the late 1800s, a scientist, commonly known as Lord Rayleigh, was trying to understand why hot objects emit light. Rayleigh knew that the color of the light depended on the temperature, like how the hotter parts of a fire burn blue, whereas the colder parts burn red. But he wanted to know where that color was coming from. During this time, the field of physics had a few perplexing problems yet to be solved, but the general consensus was that with more detailed experiments and more deeper applications of Newtonian mechanics, all of those problems would soon be solved. Little did physicists know that to solve these nagging problems, the entire foundations of physics would need to change. Not only that, but the coming solution would fly in the face of all preconceived notions on how the universe worked. This problem became known as the ultraviolet catastrophe. Without undergoing this massive shift in understanding, many of the technological innovations of the 20th century could not have been possible. We know that when light interacts with an object, it can either be absorbed, emitted, or reflected. Rayleigh considered a model object, which could only absorb and emit light, but could not reflect it. We call this object a black body. This is a model object and does not truly exist in nature, but there are many objects that are close enough. Incandescent light bulbs, hot coals, and stars like our sun are all well modeled as a black body. We call the light that is emitted from these objects black body radiation, and it turns out that the amount of radiation emitted depends only on the temperature of the object. These graphs show the spectrum of the black body radiation, which is the intensity of the light at each different wavelength. All waves have a characteristic wavelength, and in the case of light, that wavelength is directly related to color, so the wavelength axis on these graphs can simply be thought of as color. Lord Rayleigh and his colleague James Jeans considered a black body made up of vibrating particles, whose energy was being directly converted into light. They could then use this model to predict how much black body radiation would be emitted by an object at any temperature. Their predictions matched the experimental findings for large wavelengths, but as the wavelengths got smaller, things went very wrong. Their theory predicted that all objects would end up emitting infinite amounts of ultraviolet radiation, regardless of their temperature. This is why the problem became known as the ultraviolet catastrophe. This was not a catastrophe in the real sense of the word, as we all know this is wrong. When you turn on your stove, you don't immediately get a sunburn. But in the scientific sense, this was a big deal. The physicist who solved this problem was Max Planck. Max Planck was a prominent physicist in the late 1800s and early 1900s. And for solving this problem in particular, he was awarded the Nobel Prize in Physics in 1918. So how did Planck solve the ultraviolet catastrophe? In order to explain the distribution of blackbody radiation, Planck proposed that all light comes in clumps that we now call quanta. The size of a quanta of energy depends on the frequency, with this famous equation, E equals NHF. Here, E is going to be the size of the clump, the amount of energy of the light that is emitted. H is a constant, like pi, which we now call Planck's constant, which this is the value. And F is the frequency of the vibrating particles. The N shows us that these energy levels are discrete, like rungs on a ladder, as opposed to continuous, as we had previously thought. Planck's idea worked. The spectrums that he predicted matched the experiments very well. His idea may have worked, but he had no idea what this work meant for the real world. See, Planck was just making the math work out, like we all sometimes do when we don't understand our homework. It wasn't until later that Einstein proposed that light wasn't just a wave, but was comprised of particles that we now call photons, that we really understood what this conclusion meant. This conclusion helped pave the way to a better understanding of the atom, and then the weird world that we now know as quantum mechanics. Without the paradigm shift that was brought on by the ultraviolet catastrophe, modern technology like our cell phone, communication grid, GPS, and many more would not have been possible.
So that was a physics major with a physics video, and that was Michael, and I'll put his name in the chat as well. And now I will give Katie the time to talk about DIG.
Hi, my name is Katie Stelling. I'm the president of the Diversity and Geoscience Club here at Western, or DIG for short. We host movie nights, we do peer advising, and we have a bunch of game nights throughout the quarter. We're open to anyone who wants to come, and we'd love to have you join us. I can put our Facebook information in the chat on the side if anyone is interested in joining. And feel free to reach out if you have any questions.
Thanks, Katie. I love that acronym DIG. We've already said that. And so the next film is by the, there's one film from a faculty member, so I'm going to post that, and she is actually here. So if you have any questions about the previous film or even this film, we actually have some of the filmmakers to answer those questions. So I'm going to show that one right now. It's called Sutra and the Living Snow Project. That was so sweet. I really liked that, like the text and everything, the artwork. So Robin, would you like to say something about the Living Snow Project, which was advertised very beautifully in that cartoon?
Yeah, thank you, Regina. So Living Snow Project is a sort of community-enabled science project that I run out of my lab with help of lots of Western students.
Oh, and Robin, I just made you a co-host, so you can share your video if you feel like it.
Okay. Hi, everyone. Yeah, so Living Snow Project is run out of my lab, and it enables volunteers to go and collect samples for my research on snow algae. So we're interested in how snow algae blooms are moving around the mountains as climate changes, and we can't collect enough, and no individual lab can collect enough samples to create a data set big enough to answer those questions. And so we get folks to kind of work together to create big data sets. And this animation was made by one of my good friends, Gretchen Leggett, who's a local artist. And she and I have done a lot of trips together, and we did a trip while I was on sabbatical a year and a half ago in the Sierras, where we took our bikes to help us get to places where we could go sample snow. So we did some bike riding with skis on our bikes and collected samples. And so that's what inspired Gretchen to do the artwork and the animation that was in the video. So yeah, and I'm happy to answer any questions that students might have, but if that's, you can volunteer for the Living Snow Project, and you can, work with me to help, run the Living Snow Project too, if that's something that's interesting to you.
My favorite thing is that you had shown me a a movie of the algae like moving, like you were like, this is what it looks like if you like zoom in. And so that, like, please students check out Dr. Codner's lab and work with her, because it's so amazing, and it's so important to like learn about this stuff that's actually with how it relates to climate change as well, right? There's a lot of stuff going on.
Yeah, and I think it's an important thing to note to students too. It's really interdisciplinary work. So I just submitted a proposal today that included a professor from geology and 2 professors from environmental science, and me, I'm in biology. And so we're all working together to understand how these alpine systems are changing, and we need people from each of the disciplines to think about it. So if you're interested in interdisciplinary sort of systems level science, that's also a good thing for you.
Yeah, so any audience questions? If you think of something after we show the next one, that's okay. You can ask questions at any time. Thanks, Robin.
Thank you, Regina, for putting this on.
And all the students, and Kayla.
And all the students, yes, it's been fun.
All right, so the next film is called, I think, Why I Love My Major. And so I'm going to share that by Jess Costanza. And I will do that right now.
A few months ago, myself and some other linguistics students were having a lunch with one of our professors, Dr. Jordan Sandoval. She was talking about the experience of not so much knowing that linguistics exists as a discipline that one can pursue, but instead having this moment of, so when did you realize you're a linguist? Linguistics weaves together this very tangible thread I can trace throughout my life. The questions I'd avalanche onto my mom when I was little, like, but what makes swear words the bad ones? The subjects in grade school that I didn't just coast through, but actually felt some curiosity about, and the sometimes all over the place approach that my brain takes to solving a problem. And I think this is why I love linguistics most, because for me, it's the field where I feel least bound to a binary of just problems and then their solutions. There's room to explore and question. We say this all the time in linguistics, and so quantitatively speaking, it seems to be true. The domains of language feel like this really cool global puzzle. I've always had this tendency to get stuck on singular, small details in anything. Why the author of a book chose one particular word, why a recipe insists canola oil will yield a preferable flavor over olive oil, talking about something I do and having to come up with examples for it. Sometimes this is fine, but others, I have someone telling me, that's not what's important here, move on. But my brain can't help but ask the question, is that tiny detail truly meaningless? I feel so at home in linguistics because it not only encourages the time we spend on these small details, it necessitates that acute attention. Linguistics asks us, what do we think is well-formed or disorderly, or more formal or casual, universal or unique? And what do those intuitions say about how we interact with and understand each other? Linguistics encourages us to be silly when we're testing out hypotheses, like with that notorious English infix, and we come across something that sounds funny. It gives us insight to how complex but methodical of a map our brains are using to navigate language. Plus, I'd never get tired of doing linguistic magic tricks for friends and family, like with English aspiration. You see their eyes light up when the puff of air they first felt is suddenly gone. And to me, I guess it really is a kind of magic.
Next one. All right, if there, this is our last film that we're showing for our film festival before we talk about the awards first and second. Oh, there is one more club. There we go. I felt it in my soul. Okay, there we go. Michaela is going to present for, I believe, Out in Science. Sorry about that.
Yeah. Hi, I'm Michaela. I use she, her pronouns. I'm the co-president of the club Out in Science, which is just a group of students and staff and faculty from Western who just like science or are interested in science or are majoring in science, who just meet up, talk about whatever we feel like talking about that day. We meet every Wednesday normally from 7 to 8, but honestly, we go until however late we want to. We have a meeting tomorrow, and we're celebrating Trans Awareness Week, which is this week. We're going to be talking about powerful trans people and current events. It's going to be very fun. We don't have a meeting next week, but we do have a meeting on December 2nd for Prep Week. It's just going to be a chill, de-stress event if you just want to talk with some people, just de-stress for right before finals, because we all know it's a really stressful time right now. So I'll put our information in the chat if you are interested in any of that. And we would love to have more people join our club.
Thank you, Michaela. So this is our last film, and it is about the 1859 solar storm. And this is another video that was created in the summer SciComm course. And it was 2 years ago when we offered this class the first time. And it's also live on YouTube, so I can also put that link in the chat here. So I'm going to get that started. And the filmmaker is here and can talk about it right after.
What would you do if we lost power for an entire month? A year? Forever? While this might seem like a dystopian nightmare, it could actually happen. The culprit? Well, it's out of our control and out of this world. On September 1st, 1859, amateur astronomer Richard Carrington noticed some interesting sunspot activity. What are sunspots? They're darker, cooler areas on the sun's photosphere, the part of the sun we see with visible light. Carrington projected an image of the sun onto a wall and made sketches like this one. He first saw an extremely bright band between A and B, which then traveled to C and D over the course of 5 minutes before disappearing. What happened across the world after that was, well, shocking. Sparks were seen raining down from telegraph wires. Telegraphers' fingers were burnt by the electrical charge. All wasn't bad, though. So what was that bright band that Carrington saw? It was actually the first recorded observation of a solar flare. Let's take a look at what exactly a solar flare is and why it caused so much mayhem back in 1859. Sunspots are caused by the sun's magnetic field. As magnetic activity increases, the field lines stretch and twist. They go too far and, like opening a shaken soda, solar material gets launched into space. In the case of the flare, this happens quickly. The Carrington event was only 5 minutes. That solar material and radiation interact with Earth's magnetic field, pushing our leading field lines back. Some of the material follows the field lines down toward the poles, which then collides with our atmosphere to create a brilliant spectacle called an aurora. Speaking of auroras, the northern ones are normally seen in the regions around here. But during the Carrington event, they were seen as far down as Cuba, around here. Now, events like this are rare, but could we handle a Carrington-level event? Let's take a look at what happened in 1989. In 1989, a large solar storm hit the Earth and, like Carrington, created some spectacular auroras. Unfortunately, it also caused a lot of damage. The U.S. experienced over 200 power grid issues in just a few minutes. It also killed power to the entire Quebec province for 9 hours, and many didn't have power for several days. Above the Earth, 1,500 satellites slowed down due to atmospheric drag. Many lost communication with Earth and tumbled out of control. Now, this storm was only a third as powerful as Carrington and caused this much damage. Thankfully, we learned from the event and have made some important changes. We now have several NASA missions monitoring solar activity. With the heads up they give us, we can put satellites to sleep and shut down electrical grids so they don't get overloaded. But as long as we keep funding NASA and keep improving our infrastructure, we should be able to survive a Carrington-level event. If the sun decides to throw us an even greater storm, well, let's just hope it doesn't. That's it.
I love that ending. And no matter how many times I see it, I love it. Okay, so are there any questions for our last filmmaker, Aaron Howard? who is here to answer your questions. If you don't have any questions, I have some questions. No? What was the hardest part about making that film?
The green screen was really finicky. So all students at Western have access to the Digital Media Center, the DMC, and they're really awesome people. They have this giant green screen that's amazing to use. But when they make a comment, listen to their comment. So when I walked in to film the globe thing, they're like, there are a lot of shadows today. Do you want to do you have some time to let us set up some more lights so we can get rid of these shadows? I'm like, oh no, I think it'll be fine. It was not fine. As you can see by the little grainy bit, the green screen didn't quite work as well as it could have. So getting rid of the green screen and putting in the digital background was more difficult than it should have been. Yeah, that was my most difficult part.
I see that there's a couple more filmmakers. I just allowed them to be panelists. So Addison or Robert, would you be interested in saying anything about your films that we showed earlier?
Oh, I see a question in the chat from Robert. Oh. So how did the ISS handle the solar storm? I don't 100% know, and I don't know when the ISS actually launched. I didn't see anything mentioned about the ISS in my research. But I do know that a lot of satellites had some issues. GPS and other navigation was thrown off because satellites weren't where they were supposed to be. But I did not see anything about the ISS.
And I just want to make a point that in this class where we make films in 6 weeks, I put together 2 students, so they were pairs. So your partner was in that film. And how was that experience?
I just Googled ISS. ISS wasn't launched until almost 10 years later. Yeah, so we worked in pairs. In our cohort, we were half STEM students and half communication students. And so the STEM students paired with communication students, and it worked out really, really well. So I was paired with Josh Seymour, also known as Seymour Science. And he was so fun to work with, and his dead stare when holding the globe was intentional. He was very, very nervous when he knew he was going to be holding up the globe and being on camera. I'm like, oh, I like that look. Do that look. Yes, I want that look in my video. And he felt a lot better knowing that he didn't have to perform or anything. He just had to be his adorable, scared self.
We got so many comments. We have a small film festival at the end of each summer, and so many comments were worried that we were traumatizing him, but I was like, no, that was intentional. Addison Brock is here and is willing to say something about his film. His film was Light. You might have remembered that earlier. We are going to have a viewer's choice. Don't forget that poll is coming, and we are going to award the first and second prize very, very soon. But go ahead, Addison, talk about your film.
Yeah, I don't have much to say. Just it was a really fun process, and I think a lot of us, at least for me as a non-STEM major, to kind of be afraid of pursuing some high-level science, and I think we should push our comfort zone a little bit with that. And so with this, I kind of wanted to take some high-level physics and kind of, just break it down for the average viewer.
That is awesome. I really like that. I think we forget that not everyone who made these films are science majors, but they love science. And that's really important, that it's not something that's just for science majors. This event has always been for all the students, and we've only gotten a few people from outside of the majors. So I'm really glad, Addison, that you made this film. So I'm going to announce the winners unless there are any other questions in the Q&A. You can still ask questions after we announce the winners, don't worry. I'm gonna actually take a breath. Are there any other questions? Everyone's just so excited. It's a lot of money. So I'm going to announce first and second, and then I'm going to launch the poll for viewer's choice because I want you all to know that, actually, you know what? I'm going to launch the poll now. I agree with you, Maya. I'm going to launch the poll now, and that's so that you can vote. Oh yeah, actually, and while you're all voting, I'm going to let Erin talk about Fizz. I don't think you got to speak about Fizz Club, or did you already? And I'm crazy.
I did not talk about Fizz. I only talked about my film. So hello, everybody. My name is Erin. I use they and she pronouns, and I am the public relations officer for Fizz. And Fizz stands for Physicists for Inclusion in STEM. And we work very hard at making our department and the College of Science and Engineering more inclusive and welcoming to all students. And we do this through general support of our friends and fellow students. We also do, we're working on getting more workshops that, you know, kind of tackle.
You know.
What? Oh, that wasn't to me. To handle, for example, unconscious biases. And we also do volunteer work with GEMS Fair. I host virtual planetarium shows all the time. It's a lot of fun. And our main goal is to make everyone we come across feel as welcome as we can, and to make the department and the College of Science and Engineering a better place than when we joined. But we are still rebuilding. We had a really slow year last year, and we are currently in the process of rebuilding. Stay tuned. We will have more information shortly that I will ask Regina to send out.
Oh, it's really hard managing all this stuff right here. So I'm trying to, I forgot to let panelists vote, the people here who are in the club. We're still voting here. And I'm actually going to close the poll right now. Did everyone vote? Hopefully everybody in the attendance, did you vote? If you didn't, do so now. Give you a couple more seconds for fan favorite. And just a heads up, like I said at the very beginning, that even if somebody gets fan favorite, but if they get first or second prize, we want to spread the wealth, so it'll go to the runner up. Just a heads up on that. Okay, so I'm going to end the poll now. All right. So for the first prize, actually, I'm going to do second prize. Second prize, which is $150 through Amazon, goes to the 1859 Solar Storm. So Erin, I got it. Congratulations. We actually didn't clap after each of the film, which makes us monsters. But your film was awesome. Again, I didn't judge them because I helped make these, and this was scores. And I want to say that first and second was very, very, very close. And there was 6 judges, so it all evened out. So would you like to say anything on top of your second place prize? Put on your CV.
Oh, it's already on my CV. Well, not the second place prize part. That's going on, but the video is already on my CV. By the way, take science communication classes because you will build a project that you can put on your CV. And Regina's awesome. And thank you to the judges. I hope you enjoyed all of our films.
So I'm going to share the results with everyone, and I'm going to share it with you, Erin, because you actually got fan favorite too. So honorary fan favorite, you win. We're going to have to relaunch this poll because everyone else is tied. So there's no runner up now. We want to give out that $100. So I'm going to relaunch that poll. And as you all are voting, I'm going to build up to the first prize. And I'm going to allow panelists to vote. Okay, so like I said before, it was very, very close. There were 6 judges again. Mostly were students, and then the other judge was our communications consultant who has done so much work on this event. And the first prize goes to Addison Brock, the video Light. And again, it was so close. It's like point somethings away. But Addison, you are great. I'm going to make you a co-host again, because would you like to say something about your win? I like to embarrass you because it's fun.
I'm pretty speechless. That was pretty unexpected. Thank you all so much. I'm glad you enjoyed it. Yeah, I don't know. Thank you. It's a lot of fun. It's a great class for sure. I recommend it to anyone.
Oh, see, like, again, I did not pick these winners. I swear to you, people. But Addison, you get one of these masks. Don't forget, I'm going to be reaching out to all the filmmakers and giving them an opportunity to pick up these masks because they're awesome.
Can I say something about Addison's video real quick?
Of course.
So I'm a physics student, and light is an incredibly hard concept because when you go into physics class, you think everything is, that's easy. I know light. I live with light. I've understood light so my whole entire existence. And then you actually get to the fine details of it, and it's so conceptually difficult. But Addison's video, the visuals and the way it was presented, it was so straightforward and using approachable terms. And it was just an exciting video, like with the music and everything. Like, it was a brilliant science communication video. And I am so glad Addison won, because Addison's video was way better than mine.
Thank you so much. That means a lot. I'm glad you enjoyed it.
So one of the Q&A comments is that congrats to everyone who submitted videos. They were all great, and I agree. And let us now show who gets the runner-up fan favorite, because Aaron, you get the honorary title, but there is a money runner-up for that. And Addison, you're getting $250. We're going to talk about this later. I'm going to end the poll right now, and I'm going to share those results, and it is Why I Love My Major. But I'm going to contact the filmmaker who made Why I Love My Major. She's going to get $100. It's going to be awesome. Are there any last minute questions for our two winners who are actually here that I can answer questions? Everyone's so shy today. I don't know, maybe Tuesday's a bad day to do this. It's too late. All right. Well, I want to congratulate all of you one more time. I'm going to edit this to make it be super engaging. Don't even worry. This recording is going to be awesome. And again, if you're interested, or you know students because you're a faculty member who are interested in making films like this, there is that summer class. I will be teaching. Hopefully I'll be teaching this summer. And we did it online this last summer, Addison. So it was kind of hard, but we still had a good time, I think. I'm just going to force you to say that. He's just nodding.
Oh yeah, it was great. Yeah.
Okay. Thank you all for being here. I really appreciate it. It's really hard to get anyone to come to any Zoom thing, so I really appreciate the whole audience here. So thank you. And I'm going to give everyone one more round of applause. So thank you. You did amazing. Everyone had helped make this event. I really thank you. So I'm going to stop recording, and I will see you all in the future.